Hi, this is Shelley Physics, episode on the relationship between force and potential energy, and we'll look at some energy diagrams as well. In this unit, we're always starting with work, and while work is a change in kinetic energy, it's also, you might recall, a negative change in potential energy. Now, work is also the relationship between force and displacement, so F dot x. There it is. We're mainly focusing on this aspect here today, this relationship between potential energy and force. You might recall in lifting an object up a certain height, the work it takes to lift that object is you're working against the weight of the object times the height. But the work done by gravity, since gravity is the force that's downward, as you lift an object up, it's not moving after you've lifted it because gravity has done the negative work done in lifting it. So that's how we get a change in kinetic energy of 0 when you go from the bottom of the lift to the top of the lift. The positive work done by the lifting force and the negative work done by gravity equals 0. So you'll notice that whatever work you do, there's a negative change in potential energy that comes out of it. Now, if that force is not a constant force like gravity, like weight, something like a spring force, then you of course need to use this version of the rule, integral of f of x dx. That's a times there, a dot product there. All right. So when this comes into play, we're not looking at a finite amount of change of potential energy. We're looking at an infinitely small amount. So you might also note that this negative delta U, in terms of a small change, a very infinitesimally small change, can be written negative du. And out of that, we get a relationship between force and potential energy that looks a little something like this. F of x, force is a function of position, equals negative du over dx. And what is that? That's the derivative of u as a function of x with respect to x. The force is also the negative slope of the potential energy function with respect to x. What is that? Well, let's take a look at it on a graph. This is a u of x graph, potential energy versus position. For gravity, gravitational potential energy, it's mgh. Now in this case, I've got an x graph, so I'm going to call this mgx. What kind of function is that? It's a linear function, a line. I'm going to draw a line here. As you lift an object up, this x becomes greater and greater and greater, and so does the graph here. So what is this expression telling us about the force involved? Well, the force involved with the gravitational potential energy is gravitational force, or the weight. So what kind of result would that give us if this is the u of x function? If we look at the negative slope, consider the negative slope of this u of x function, what kind of value we get? Well, the slope itself is a positive slope, and it's constant. So this is a positive constant slope. Well, the force is the negative of that slope. That means we're going to get a negative and constant force out of that. Isn't that what gravity is? Weight is a negative constant force here at the surface of the planet. All right, well, what about, let's try out springs. What about a spring? With a spring, the u of x function is 1/2 kx squared. What kind of function is that? That's a quadratic, right? Curves up something like that, more or less. As x becomes greater, then the u becomes greater. This is for like an elastic potential energy here. And so what about the force? What would that look like? F of x equals negative du dx. Now in this case, we don't see it as a constant, but what's happening with the slope? The slope is increasing as x becomes greater. Doesn't that happen also with the spring force? The magnitude is kx. As x becomes greater, the force becomes greater. Isn't the slope becoming greater as x becomes greater? It is. But remember, Hooke's law is in the opposite direction, is a negative force. It's a negative kx. So we also have a negative force acting here as a spring is pulled outward and displaced outward in the positive x direction. There's a positive change in x this way. The spring exerts a force back in this direction. All right, so there's a negative force there as well. So this works as well for that. Now, what if we're working with a force versus displacement graph? Is there a way to compare a force displacement graph to potential energy? Well, if we write this expression out, f of x equals negative du dx, let's bring it back to the form of integration. We'd have a negative du. If I multiply both sides by dx, that would leave us with an f of x dx on this side, and we'd integrate it on both sides like this. So what would the change in potential energy be then? Bring the negative over, multiply both sides by -1. The change in potential energy would be negative integral of f of x dx. In other words, the negative area. Remember, this is the area. We're dealing with slope of the potential energy function over here. Here we're dealing with the area within the f of x curve. Now remember, that's related to the work done. Work is negative potential energy. For our spring, if this is a spring force, F equals kx, at least in magnitude. All right, and if we start looking at this now, F of x dx is equal to potential energy. If you ever ask what's the change of potential energy from x1 to x2, so from starting position to some final position over here. If we stretch that spring out, that's going to be the area underneath. Let's extend this upward, and we're going to just find the area within there. That's going to be the change in potential energy, but the change in potential energy of the spring itself is going to be that negative change. Don't forget the negative in here, okay? Negative change of potential energy. What about coming back to the gravity, okay? Well, gravity is a constant force, mg. So what's the change of potential energy as we lift up an object? Well, the force as a function of position is just a constant, mg. That's all that's going to be. And if we go from some x1 to x2, here's x1 position, we're going to some x2 position. Now we're going to lift it up from near the bottom of the hill to the top of the hill. What's the work, or what's the work done, but also what's the change in potential energy going to be? Well, change in potential energy is a negative f of x dx. This is just the area underneath the gravity, the constant gravity curve. Since gravity is not distance dependent, it's going to be a constant. So if we find that area right in here, from x1 to x2, easy thing to do, it's a rectangle. And just note that that potential energy due to gravity will be negative mg as the y-axis times x. And this would be x2 minus x1 right in there. So whatever that difference between x2 and x1 is, times mg on the y-axis, that would be the area. That's change in potential energy. All right, what about an actual function? Let's give a go to my other page here. What if we have a kind of an unusual one here? Let's go 2x squared plus 4. And we'll do the u later on. What will be the change in potential energy under this curve from x equals, we'll go 2 meters to 4 meters. Well, with this curve, it's going to be a quadratic. And 2 meters is about here to 4 meters over here. That gives us an unusual kind of area, so we're probably going to have to use our integration tool. Change in u equals negative f of x dx. We're going to plug in our limits, our bounds here, from 2 to 4. And the function we're given up here is 2x squared plus 4. Integrate here, it's be x cubed over 3, so 2x cubed over 3 plus 4x would be the integral of that, and we're going to take that from 2 to 4, and oh, don't forget your negative. We're going to need that. And we're going to plug that in. 2 times 4 to the 3rd power divided by 3 plus 4 times 4. I'm going to go ahead and put a bracket in here. Minus 2 times 2 cubed over 3 plus 4 times 2. There's the whole integration. We'll have this prevailing negative out front. 4 times 4 is 16, times 4 is 64, times 2 is 128. And here we're going to have a minus. 2 times 2 times 2 is 8. It's 16. So negative 16 thirds plus 8. And we'll simplify. 128 minus 16 is 112. I got the plus 24 over here. And 24 times 3 is 72. I think that looks right. Be 184 thirds. And that is not divisible by 3, so we're going to have a little bit of change left over. 183 is divisible by 3. I have no idea what that is, but we'll just call it 184 thirds. And we're missing one important thing. I dropped off that negative. I'm doing this on purpose because that is often forgotten. Don't forget about that. Joules. There we go. That's the potential energy done by that force function. What about if we have a u of x? Let's make it a little bit different here. All right, that's our function. Again, it's going to be an upward facing quadratic with this negative x plus 2x squared. We're starting at 0 with a 1. This is going to be negative 1 plus 2, so it does start out positive and it increases somehow, however that is. So my question here is, what is the force function going to look like? What's the force function going to be for this u of x function? Force function is negative du dx, which is the negative slope, or the negative derivative. So let's go ahead and work that out. We're going to take negative d of negative x plus 2x squared dx, derivative of, I have a negative here, Derivative of negative x is -1. Derivative of 2x squared is 4x. So we're going to have a force of -4x, we're going to apply that here, plus 1. That's our force function, -4x plus 1. All right, so there's just an example of the two. Looking for area if you've got the force function, looking for the slope if you got the potential energy function. But just know that they're interchangeable. It's a very calculus concept, and you can always go to it. Your equation on your AP Physics equation sheet looks like this. Here's the equation sheet. You have to zoom in a little bit. Let's make this bigger. And right here is the expression that you see for it. Change in energy equals work equals integral of F dot dr. When you're going to interpret that on your own, that's all you ever got is on your own. It's got change in energy is work. And remember that change in energy, of course, is a negative change in potential. It's also a change in kinetic energy. That's where it all comes in. And it's got a integral of F of r dr. This is the entry on your equation sheet. So what do? How do you work with it? You note that the negative change in potential is energy. You do need to remember that piece, and that's equivalent to this F of r dr. If we drop that integration sign and turn this to a negative du, then you've got your expression. That's the one we're looking for. It's there on your equation sheet. Some of these equations you have to dig around for. You got to know when to use it and how to use it. But that's what this practice is for. Please take this with you into your next set of book problems. I hope this has been helpful.